Okay, so first question we're going to take a look at, they're going to give us a formula. So this is a formula for exponential growth. And we have 150 bacteria doubling, and it doubles every hour. Okay, so that would be written down in the problem. The amount of bacteria doubles every hour. So I want to find two different things. One, how many bacteria will I have after 10 hours? And then two, how long does it take to reach 10,000 bacteria? So the difference is where you plug the number in. Okay, so we got to make sure we know just where to put it. So let's start with part one. Okay, so part one, you're finding the amount of bacteria after 10 hours. So where would the 10 get plugged in? Yeah.
The X.
Yeah, the 10 is going to get plugged in for the X. So the amount of bacteria after 10 hours is going to equal 150 times 2 to the 10. Right, so we'll plug it in and see what we get. So 150 times 2. And you can type it in without any parentheses because it's a simple enough expression. The calculator will handle order of operations fine. Okay, so we get 153,600 bacteria. Okay, any question on part one? All right, now part two, it's asking how long before we hit 10,000 bacteria. Where's the 10,000 going to get plugged into that formula? Yep.
AFT.
That's AFT. So we're going to change the left side to 10,000. And then the right side is just going to be 150 times 2 to the x. Now, we haven't learned yet how to solve equations that have variables in the exponent algebraically. That's where logarithms come in. We learned how to do it graphically. So what would I type in? Jose, what would I put in y1?
10,000.
Yep, 10,000. And what could I put in y2? Yeah.
150 times 2 to the x.
Times 2 to the x. Okay. Now, the minimum amount of bacteria that we're going to have in this problem is 150. Can't go any lower than that. And we want to know when we're going to reach how much bacteria? 10,000. So let's go to 12,000. X is the amount of hours that have passed. What's the smallest amount of hours we could have that have gone by? 0. And the largest amount of hours, well, we don't know. We just have to go far enough. What we know, if we go to 10 hours, we're going to hit 153,000 bacteria. So it's less than 10, okay, when we hit 10,000. So we can leave it at 10. That's fine. But it's definitely going to be less. All right, so there's our bacteria increasing. And what do we need to find now?
The intercept.
Yep, we're going to find the intercept. So second, calc, intersect. And it's going to take about 6.06 hours. And again, I put approximately because that's not an exact answer. It's just an estimate. Right. So any question on the first one?
Can I see the window?
The window? Yep. So there's your graph. And there's your window. Okay, so next problem is solving a radical equation. What's the first thing you have to make sure of when you start solving a radical? Yeah.
That the square root, the radical is by itself.
Yeah, whatever the radical is, square root, cube root, we got to make sure that it's by itself on one side. Is it by itself here? No. What could we do on both sides that would get the radical by itself?
Subtract 3.
Yep. So we're going to start by subtracting 3. And we're going to get the square root of x minus 4 equals 9. Okay. So we got we got the radical by itself. Now we're ready to do something to get rid of it. What would you do on each side to get rid of that radical?
Square both sides.
Yep, we're going to square both sides. So you raise each side to whatever power would cancel your root. If it's a square root, you square. Cube root, you cube. Okay, what does that give me on the left?
81. Or x minus 4.
Yeah, x minus 4. And then on the right we get 81. And that means x is going to be 85. Okay, we always want to make sure we check it and make sure that it works. We've checked some that don't work and some that do. So let's see. What's 85 minus 4? 81. And the square root of 81? 9. That's the positive square root because it doesn't have a negative symbol. So 9 and then plus 3. 12. Perfect. So that answer works. That's how you solve a radical equation. Any question on that? Okay, so this one we're looking at solving a rational equation. And the way that we want to do that, we want to multiply everything by the least common denominator. Now the hope is that what's on the right is the product of the two that's on the left. What can we do to the denominator on the right to see if it is the 2 on the left? Yeah, yeah, we can factor it. So let's factor it. We need an x and an x. We have a positive in the middle and a negative at the end. What does that mean my signs would have to be? Yeah, you'd have to have a plus and a minus. And two numbers that multiply to give me 2, well, it's got to be a 1 and a 2. So I would try... No, that's not going to work. Let's try it the other way. Let's try a 2 and a 1. So that's going to give me negative x plus 2, which is plus 1. Perfect. So that the product of the two denominators on the left is the one on the right. So that's going to make it a little easier. Okay, now we just have to figure out what to multiply everything by. Yeah.
What do you multiply by x plus 2 times x minus 1?
Yeah. X plus 2. X minus 1. And we're going to do that in all 3 spots. And something's going to cancel everywhere. In the first fraction, what's going to cancel out? X plus 2. Second fraction?
X minus 1.
X minus 1. Third fraction?
Whole
thing. So all we're left with on the right side is a 5. If this turns into a quadratic, we're going to want to bring that over and get it equal to 0. So we'll see what happens. We have an x minus 1, and we have to distribute the 3x to it. Okay, what do you get if you distribute 3x to x minus 1?
3x squared
3x squared
minus 3x.
minus 3x. Now in the next one, always be careful with this symbol, right? It's a plus, so it doesn't affect anything. But that is what you're distributing to the next one, plus 2. Okay, so that's going to give you 2x plus 4. All right, is that a quadratic that we have to solve? No? Yes?
Yeah.
Yes? All right, I got 2 yeses and a no. So I'm going to go with the yes. So yeah, that is a quadratic because the highest exponent is a 2. So we want to combine everything and get it all on one side. What's negative 3x plus 2x?
Negative x.
Negative x. And let's bring the 5 over. What's 4 minus 5?
Negative 1.
Negative 1. Okay. Now, to solve a quadratic, one method is to try to factor. We did that earlier, some factoring. Or we can use the quadratic formula. I don't think we're going to be able to factor that because you're looking for 2 numbers that, well, it's got to be a 1 and a 1. Well, let's try it. Well, I don't know. Let's see. 3x of x has to be a 1 and a 1. And what do my signs have to be?
Plus minus.
Yeah, plus and a minus. So if I try like a plus and a minus, that gives me negative 3x plus 1. Well, that doesn't work. If I switch them, it's still not going to work. So I don't think it's factorable. Okay, so how are we going to have to solve it if we can't factor? Yep. Okay, what's A going to be?
3.
B?
Negative
C?
1.
Okay, so we got negative B plus or minus the square root of B squared. And what comes after the 4? 4 times
A times C.
A times C. 3 times negative 1. And we divide by
2A.
2A, which is
6.
6. Okay, we are subtracting a negative number under the root, so we can make it addition. And what does that give me for the radicand? What's 4 times 3 times 1 plus 1? 13. There you go. Those are your two answers. We just have to make sure that when we plug them back in, they don't cause you to divide by 0. There's only 2 numbers here you could plug in that would cause you to divide by 0. What are the 2 numbers?
Negative 2 and 1.
Negative 2 and 1. That's not a negative 2 and that's not a 1. So that answer is fine. Well, answers. There's 2 of them. Okay, on the test, if you get 2 answers like that, you can't use the plus or minus symbol. So you're just going to have to type 1 plus root 13 over 6 in one box, and then 1 minus root 13 over 6 in a different box. Any questions about it? Okay, so this one's going to be describing the transformations of a radical. If we were doing it for an exponential, it would be the same basic thing. First thing I like to figure out is how many transformations I think I have. Okay, so what do you guys think? How many transformations there are?
4.
Yeah, there are 4. We pretty much have a number in every spot that we could. So we'll have to describe all of them. What's the first transformation we would describe? Yep.
Horizontal shift to the
Yep. Shift which way?
left.
Yeah, that's going to be a shift left 4. Okay, so shift left 4. What's going to happen next? Right, we have a because it's inside the root, so that's a horizontal reflection, or you can say reflect over the y-axis. Okay, so that's the second one. What's the third one?
Vertical stretch by a factor of 2.
Yep, so we have a vertical stretch by factor of 2. And what's the fourth thing that's going to happen?
Downward shift A.
Yep, shift down. So in terms of describing transformations, that's pretty much what I'm looking for. I could do it a different way. Instead of giving you the formula, I could describe all these to you, and then say, give me a formula that does that. Shifts left 4, reflects, stretches, and shifts. Any questions on that one? Okay, so in this one, all we're going to do is graph the function. And the way the question will work on the test, it'll be like a match. So you'll just have to graph it and see which one it looks like. So really the only thing that could go wrong is if you don't know how to type it in. Nothing special, just 3 raised to the x minus 1. That's pretty much it. Depending on the graphs I show you, you may have to change the window. So if the window on the test shows from like negative 20 to 20 on the x-axis, then you'll have to change yours negative 20 to 20 to make it match. Okay, I'm just going to do zoom 6. And what is that x minus 1 doing? Like if it was just 3 to the x, it would look a little different. What's the minus 1 doing? This ties in with the transformations. Yeah.
Shift to the horizontal shift to the right.
Yeah, that's shifting it to the right 1 unit. Okay. You can tell that it's shifted to the right because if you graph 3 to the x, the graph in red should look like it's a little bit to the left. You won't be able to tell there, but now you can tell. It's moved 1 unit to the right. Right, so it would just be a matter of matching it up to the picture on the test. So any questions on how to type in a exponential graph? Or exponential function? Okay, so the next one we're going to look at is a radical function, and they want us to describe some things about it. Let's start with the y-intercept. How do you find a y-intercept in an equation?
Don't find the x and plug it in.
Plug in what for x? Yeah.
Having 0, right? Because that's
Yeah.
what you said.
You plug in 0. Just think about a y-intercept. If you draw a graph, where the graph crosses the y-axis, this coordinate is always going to have a y. Sorry, I messed that up. It's always going to have an x value of 0. Every y-intercept is always 0, comma something. Right, so we fill in 0 for x. Okay, let's try it. What's 2 times 0?
0.
And then plus 4.
4,
And the square root of 4?
2,
2, and then minus 5.
3.
Negative 2. So there is your y-intercept. If this graph had been shifted up 5 units, it's possible, actually no, it still would have had a y-intercept. If the graph had been shifted to the right, it would not have had a y-intercept because it would have looked something like this. It would have been shifted down 5 and right, and it would have never crossed the y-axis. Okay, so the domain. What part of that do we have to focus on when we're looking at the domain? Like there's something there that doesn't matter at all, and then there's part of it that does matter. What's the part that does matter? So the part under the square root, what does that have to be? It can be 0. You can take the square root of 0 and you'll get 0, so that's okay. But it can't be negative. So it has to be greater than or equal to 0. So to find the domain, make sure that your radicand is always greater than or equal to 0. So that means x would have to be what to make sure that it's always greater than or equal to 0?
Greater or equal to 0, negative 2.
Greater than or equal to negative 2. Yep. That's your domain. You could write the domain as an inequality, or you could write it as an interval. So if you want an interval, there you go. Negative 2 to infinity. Okay, so any question on the domain? Okay, now the start point. It's kind of similar to what we did with domain. The start point has an x and a y. How do you find the x value of your start point? Remember what we did for that? Not sure. Yeah?
Actually, I don't know.
Not sure. Don't have a guess? Do you have a guess?
No.
No.
Would we?
What's that? No, you can't do a minimum because the square root function never changes sign with the slope, because the square root function is always, like in that case, it's always a positive slope. To get a local minimum, you have to go from a negative slope to a positive slope. So we can't do any kind of local minimum. Have another guess? Do you have a guess, Lena, maybe? No?
No.
So to find the x value of the start point, you have to set the radicand equal to 0. That's how you find the start of the x. So you just set, that's why I said it's similar to what we did with the domain, except we don't want to know when it's greater than or equal to 0. We want to know when it is exactly 0. Well, we pretty much already solved that. It's going to be when x is -2. Now, you still have to find the y value of your start point. So what do you do with -2 to get the y value of the start? Right, you plug it back in for x. And then 2 times -2 will give you?
-4.
Plus 4?
0.
Square root of 0?
0.
And then -5.
-5.
So the -5 is all that really matters. So this particular graph has a start point at -2, -5. Now the calculator may not show that because it gets kind of steep there, so it may look like it's different. So you have to know how to find it yourself. Now, why did I have, I could have wrote center point. I should have asked you that. How do I know that this is a start point and not a center point? Yeah. Yeah, that's an even index, right? It's an even root. Even roots always have a start point. Odd roots have a center point. Since odd roots go in both directions, what's the domain for any odd root?
All real numbers.
It's all real numbers. They go left and right forever. But even roots do not. So any questions on finding those? Yeah.
Is the x for the start point always what the domain is?
Is the x for the start point? Yeah, it's pretty much how you would find the domain. The only difference with the domain is this could be either a bracket or a parenthesis. But basically the number that you put there, well, there, is the number you're looking for. Yeah.
How did you know that y equals -5?
Because we plugged in -2 for x and then did it out.
For that whole thing?
We did out that whole thing. Yeah. But this is all 0. Because we know we found -2 to make sure that that was 0. That's what we set it equal to. So the only part that really matters for the y is what's at the end. Yep.
I have a separate question about this one.
Yeah, about a different one? Sure. A one we did before? Oh, another one coming up? Or
Yeah,
just one
like
you
a
have?
question about like something in general.
Sure.
Like when you have like x plus 3 over 2x minus 7, and then it's like less than or greater than or whatever, 5 on the other side. Like when you want to set it so that it's like equal denominator, like how do you multiply it or add it, or like do you? I don't know how to like say it, but it's like.
So if you had something like this, like that. So to solve that, you have to get 0 on one side. So when you do that, I mean, you can do that. That's okay, because now you have 0 on one side, but you need a common denominator here to be able to add those two, or in this case, subtract them. So the common denominator is going to be x minus 2. So you multiply the 4 by x minus 2 on the top and x minus 2 on the bottom. So it ends up being this. And now we can put everything as one denominator. So the x plus 3, that stays the same. But then you have to distribute -4 to each of those. So now it's -4x plus 8. Now you can combine like terms and make your sign charts and then go from there. Okay, so to solve an inequality graphically, you just put one side in y1, put the other side in y2. So we're going to put in 3 to the x and 4 to the x. So I'm looking for where the graph in blue is on mine, is under the graph in red. So there's the graph in blue. And here's the graph in red. And I'm looking for where the graph in blue is under the graph in red. Well, does it look like the graph in blue is always under the graph in red?
No.
No. So then at some point, it must cross it. I know it's a little hard to see, but where do you think the graph in blue and the graph in red are crossing? Yep.
0, 1.
Yeah, they cross at 0, 1. So they cross right there. So now we want to write down when 3 to the x is below 4 to the x. So you want to describe that using x. So when x is 1, the graph in blue is under the red one.
When x is less than 0.
So when x is less than 0, the graph in blue is under the red one?
Sorry. When x is greater than 0.
Greater than 0. Yeah. As long as x is greater than 0, the blue one is under the red one. Yep. If it had the inequality flipped, it would be what you would say first. Okay. So any questions on solving that graphically? Yeah.
Are those like the only two answers that you get? Like x is greater than 0 or x is...
No, if you shifted it left or right, that could definitely make a difference.
So if it was like 3 minus...
So yeah, if you put in...
3x minus 1.
Yeah, if you put in like a -1, that's going to shift the graph of the blue one to the right one. So now, let's see what happens. Okay, so now there's your blue one and your red one. So if the blue one goes to the right one, let's see. So it moved right. So that means they're going to cross, I think they're going to cross earlier. So let's just do the intersect because it's such a thick line we can't really see it. Let's do second calc intersect. So I think it's going to be further to the left that they cross. Yeah, so now they cross at -3.8. So just by shifting it right 1, it really messes up where they cross. Yeah. So now, yeah. What I would do to see that a little better if you needed to is set your y min and max to like -2 and 2. And then I think you would be able to see it better. Because they get flat so quick, you can't really tell. Now, well, it's still hard to tell even zooming in that much. It's very hard to tell. Any other questions on that? Okay. So this one, we're first going to just determine if f of x equals 3 to the x is a growth or a decay function. Which one is it?
Growth.
Yep, it's growth because the base is bigger than 1. So it's growth. So growth is going to look something like this. So the first thing I have describing the end behavior is as you head to the right, what's happening to the y value? That's the top one. So what happens to the y value as you head to the right?
It goes on forever.
And what does it approach?
Infinity.
It approaches infinity. Now, I don't have an axis in here, but let's pretend like this was my axis. This just keeps going like that. As you head to the left, what does the y value approach?
0.
Yep, 0. Okay, so that's describing the behavior as you head on each end. There'll be a couple questions like that. Questions on that one? Okay, so the last one, they want us to find the number of local extrema. So how do we do that? What do we have to do with f of x? It's not really something we do algebraically. You can do it algebraically, but you need calculus to do it. So it's something we've approached a little differently. Yep.
Would you just plug into the calculator?
Yeah, we're going to plug it in, and we're going to graph it. And remember what local extrema are. They're local minimums or maximums. So a point that's higher than everything around it or lower. So x to the fourth plus x cubed minus 2 and then let's do divided by x squared plus 12x minus 30. All right, let's do zoom 6. Okay. So, what do you think? How many local extrema does that have? Might have 2. I'm not really sure what's going on the y-axis. I'm going to have to zoom in. It definitely has 1. I can see a local minimum right there. Now, it looks like there might be a maximum in the part that's close to the y-axis. Or maybe even there's another minimum. Maybe it dips down and goes up and comes back. Who knows? All right, so let's graph it and let's zoom in there. Okay, so the point of this problem is you need to either zoom in to kind of see what's going on, or sometimes you need to zoom out. Okay, because imagine this part is like way up there. If you do zoom 6 and that part's way up there, you might not even think to look for it. So you always want to make sure you zoom out enough to see what you're looking for. Okay, I'm even going to, you know what, before I zoom in, I'm going to set my Ymax higher. I'm going to set my Ymax to 40. I'm going to set my X min. I'm going to try negative 20. I want to see something. Still not convinced that there's only 2. Because what's the difference between the degree in the top and the degree in the bottom?
2.
It's 2. That means that this graph should have a parabola shape to it when you zoom out enough. I'm still not seeing like this parabola continue the other way. Right? It should be. So I'm going to try, I'm just going to keep trying to zoom out. Let's try negative 40. And let's go up to 120. I thought I would have seen the parabola continue the other way at some point. Let me go and try one more thing. Let me go to my table. And let me set x to a value that's way on the left and see if it ever jumps back up into the positives, or does it just keep going down? So let's try like negative 80. Okay, so when you hit negative 80, it was up at 7,000. So there's something else going on in the graph. Right? I'm just not finding it quickly. Let's try like 3,000. Aha, there it is. So I knew there was something else, and there is another local extrema. So that one was really tricky. The only way you would know to look for another local extrema is the fact that the difference here is a 2, and the shape of this graph should be a parabola, and I wasn't seeing the other part of it. So you get one local extrema here, you get one over here, and did anyone look in the middle and see what was going on?
Okay.
That's it? All right, thank you. Did you submit?
Yes.
Okay. Just tell me what's going on in the middle.
I think there's a little up, maybe 2 of them.
There's 2 in here, you think?
I think so.
Let me see what you
I
have.
used the Zoom.
See, so could be what I would even do is set like your y min at like negative 0.1 and set your y max at positive 0.1, and then that should really show what's going on. So it looks like there is a y max, but I think there is only one right there.
Okay.
I don't
It doesn't
ever.
matter that it goes down a little bit, like, because that looks like it's going down and it goes back up. Just not by much. Or is that like, I don't know.
It still always stays positive though. So if it goes like this, it goes like this and then like this, that's not a local minimum there. To be a local minimum, it would have to do like that. It would actually have to go from being positive slope to then turn and go down.
Okay.
And I don't think it ever does that.
All right.
So I think on this one you're gonna get 3 local extrema.
Thank you.
So I'll say, yeah, you're welcome. So the point is, make sure you zoom out. Because I bet a lot of people, I bet almost everybody would have put 2 for that one. They would have missed this one way over here.
Can you